All right, inverse functions, 1.5. So inverse function notation looks something like this, right? With a f with a little with -1 up top. But it looks like kind of an exponent, but just -1. And this is our normal function notation. This is what our formal inverse function should look like. Now, to define an inverse function, we need to talk about composite functions from last section, right? Because really, if two functions are inverses of each other, they can do this. The inverse function of f of x should equal x, and then also the other function, f of the inverse function, should also equal x, thus making them inverse of each other. One thing to note with inverse functions, so let's say f of x, its domain must be equal to the inverse function's range. And then the f of x's range must be equal to the inverse function's domain. Okay, that's going to be important as we are using some notations and trying to find a domain and range of functions. We need to keep that in mind. If we're given a domain for the original function, the f of x, we know that's going to gotta be the range of the inverse function. All right, so let's show that these two functions are inverses of one another. So I'm going to find f of g of x, and I'm going to find g of f of x, and they must both equal x in order for them to be inverse of each other. So f of g of x will be 3 minus 4 times the quantity 3 minus x times 4, or I'm sorry, divided by 4 rather. 4's cancel, so I'm left with 3 minus parentheses 3 minus x. 3 minus 3 is 0, and negative of x is x. So yes, that's so good so far. Now g of f of x, let's put in f of x everywhere we're seeing x. So it'll be equal to 3 minus parentheses 3 minus 4x over 4. 3 minus 3 is 0. Negative of negative is positive, so it's 4x over 4, which is x. So yes, they are inverse of each other, and we just proved it now. Now, using the same two functions, so we know they're inverses of each other, but let's prove this graphically. How can we do that graphically? So let's pick some points. When we have f of x, let's make a quick table. Table of values. Let's say we have -1, 0, 1, 2. When we plug those in, what do we get? We get 7, 3, -1, -5. So with inverse functions, if two functions are inverse to each other, if your x's and y's flip, right? When we talk about domain range, same story here. So if we have x's, these are x's, these are y's, it should be the case that when x is equal to 7 over here, your output should be -1. Okay, so the x and y should flip. So let's test that out. So I'm going to test out, this is for g of x. This was for f of x. So if I put 7, 3, -1, -5 in, let me make my 7 a little better. That's because we're going to get a guess. We put that in, what do we get? Yes, we do get -1. We do get 0. We do get 1. We do get 2. So it doesn't work out. So yes, we showed even though we didn't actually graph it, but as you can see, if we swap the x's and y's, it should work. Another thing to note, if we were to actually graph this, it would reflect over the line y equals x, okay? So all of our points would flip over y equals x. So we are going to use the horizontal line test to tell whether a function has an inverse, okay? So we have y equals x squared plus 2. So if I graph that, it'd look like that, right? More or less. Now, what is this horizontal line test? So you might, or hopefully you remember the vertical line test, right? Where if I went through and if any x value has multiple y values, that was not a function, right? So if we remember, if the inverse has any two of the same y values for two different x values, then it's not a function, okay? So it's, because remember, inverses, the x's and y's flip. So instead of it being the vertical line test, it's a horizontal line test. So is there any point that for any given y value there's multiple x's? Oh, yes, there is. So this does not have an inverse function. No inverse. Now, a little warning. So you might be still asked to find the inverse of this on a homework, okay? Now, one thing they tend to do whenever you do this is that they might say for the domain of x greater than or equal to 0. Because at x greater than or equal to 0, that's only this part of the graph, right? So it does pass the horizontal line test if that was the case, right? But it didn't say that, so therefore we say no inverse. But I'm just saying, you might be having to find the inverse of an x squared function or something that doesn't pass the horizontal line test because it might have a domain or something. Now, one-to-one functions. Let's talk a second about that, one-to-one. One-to-one functions are basically what I was just talking about with this horizontal line test. A one-to-one function is if each value of the dependent variable corresponds exactly to one value of the independent variable, meaning dependent depends, right? So the dependent variables worried about the y. Independent is the x, right? So if any given y value has exactly one x value, it's one-to-one. That wasn't the case here, right? Because we had y values with multiple x values. So one-to-one function, I'll say it again. Each value of the dependent variable corresponds to exactly one value of the independent. So if this function was one-to-one, we could find the inverse, but it's not. All right, so we have two functions here. Let's find the inverse, what's called analytically, meaning I'm going to show you that now. It's a process in order to find what the actual inverses are. So what I'd like to do first, make f of x y. Y is easier to work with in these types of problems. Now keep in mind, as I warned you in the last slide, we have here x is less than or equal to 0, so since that's the case, we can actually find the inverse. Next step is swapping the x and the y value. So x equals y squared minus 2. We are now trying to isolate y. So I'm going to add 2, x plus 2 equals y squared. Now keep in mind when we are because our goal is to get y by itself again so we can find the inverse. When we square root both sides of an equation, we always include the plus or minus in front of the square root, right? But keep in mind, I'm going to hold off on doing that for a second until I explain this. Keep in mind the domain of your original was less than or equal to 0. I gave you that in the beginning. What does that mean for us? That means the range is less than or equal to 0, right? So since it must be negative, your output must be negative. Therefore, I'm putting a negative sign in front, okay? All because of what the domain said in the beginning. Right here, it said x is less than or equal to 0, so therefore, my range is y is less than or equal to 0. We got another one here. I didn't finish this one. I need to make sure I put it in proper notation. Look at that. Looks nice. All right, next one. Swap the y and the x. X equals y plus 1 over y minus 2. I'm going to multiply both sides by y minus 2. And I'm going to distribute the x. Now you might be thinking, oh no, we have multiple y's. Well, we can fix that here. What I'm going to do is put all the y's on one side and all the non-y's in the other. So add 2x, minus y, xy minus y equals 2x plus 1. Now that I have all the y's on one side, I can factor out a y. And then divide by x minus 1, giving me a solution of, I'm going to write it up top. The inverse of f of x is equal to 2x plus over x minus 1. Now let's talk domain and range. Domain for the original was all rows except for 2, right? So it would be domain of this is going to be negative infinity to 2 and 2 to infinity. Which means the inverse function, I'll use blue for the inverse function, the range of the inverse, so that's range, boop, boop. The range is going to be the same thing, right there. Okay, it's going to be negative infinity to 2 and 2 to infinity. The range, if you were to graph this, you'd see that it would never touch y equal to 1. Okay, how do you know that? Well, we'll talk more about this a little later, but anytime we have the same power here, highest power is the same, look at the coefficients, 1 divided by 1, it's never touching 1. Okay, so therefore, the range is negative infinity to 1 and 1 to infinity. Thus, this is the domain of the inverse function. So domain would be the same thing. All right, last problem. So I'm giving you f of x and g of x, and we're going to kind of combine like last two sections into one problem. So we're going to find the inverse of f of the inverse of g of x of 1, and then we're going to do a similar problem below with just f of x. So let's find the inverses first. That might help us. Now I don't have a ton of space here. So if I swap x and y, it'll be x equals 1/8 y minus 3. Add 3. You're going to go over here. X plus 3 equals 1/8y. Multiply everything by 8. And the inverse of f of x is going to be equal to 8x plus 24. Now g of x's turn. I'll use a different color. Let's use green. X equals y cubed. Cube root. Y is equal to the cube root of x. Now find f, inverse of f of the inverse of g of 1. So work right to left when doing composite functions, okay? Right to left. So I'm putting 1 into the g of x, which I did not properly label. Should be down here. Put that 1 in. What happens? That's going to get us third root of 1, which is 1. So we're putting 1 into the inverse of f function. So f inverse of f of 1 is equal to 8 times 1 plus 24. 1 times 8 is 8, plus 24 is 32. So the answer to that one is 32. Now for the other one, put 6 in first. 8 times 6 plus 24. Get you a really big number. 48 plus 24 is 72. We're going to do it again. 8 times 72 plus 24. This will equal 600. There we go. Thank you for watching, and we'll see you in class.